My name is John. Today I'm going to talk about the project that I've been working on for the last few months. This project was actually my bachelor thesis for University of Vienna, and my supervisor was David Hahn from Technical University of Vienna. With that, actually, we can begin. I hope I can switch it, okay. Here is the rough outline for the presentation. I will first introduce the essential ideas we utilize in our project, and then continue with the problem and goals, and then switch on to the method, our approach, and specifically going to talk about the optimization process we implemented. And in the end, hopefully, I'm going to show the results, pretty nice results in the end. So with that, let us actually begin. Especially in this conference, rendering is a relatively well-known problem. We have some input. This input is often a scene description, contains geometry, materials, lights, etc. And rendering is a process that maps this input into another vector. In this case, it's an image. However, in today's talk, I would like to talk about the opposite of this process, which can be called inverse rendering. And the idea is to acquire a material description, or actually scene description, from a given set of reference images. However, please note that this process is actually not directly invertible. We are in a physics-based rendering setting, so there are a lot of difficulties. With that, let me switch to the difficulties. So this is a photograph, and I'm not going to talk about the whole effects that you can see here. But intuitively, one could think the problem isn't that difficult. So for example, we see a red book object in this photograph. And one could say, okay, the scene description should then contain a book object with some red-colored material. However, we would like to describe reality in a physically accurate manner, so that would be really a basic assumption. So for example, the red pixels that you see in this photograph, there could be a lot of reasons why they are the way they are. So in the most simplest case, that would be true. We can say that the scene description should contain a red-colored material. However, you can also see some red pixels on top of the laptop. So we can't really, that's why we can't really say directly, or we can directly invert this process. With that, let me switch to the objective function. So that's why we basically convert our task into an optimization problem. And with this, we actually introduce an objective function which quantifies the current quality of our solution. In most simple cases, we actually introduce the L2 error, which basically the difference between our current rendering and the provided reference image or target. So basically, the idea is plugging in the rendering function inside this objective function to try to close to the provided reference images. With that, let me switch to differentiable rendering. So since the domain we are in is quite high dimensional in physics-based domain, we actually convert our problem even further into a local optimization problem using gradient descent. So the idea is taking a differentiable rendering step and plugging this into an objective function to quantify our current solution, or current quality of our solution, and then somehow differentiate this whole rendering process to acquire the gradients and get close to the provided reference images. However, differentiating this whole process is extremely memory consumptive. So fortunately, Mitsuba is the primary renderer that we use, allows us to use the chain rule, which first of all, we actually differentiate the objective function, and in the L2 error, in the case of L2 error, which is an image like this in the middle, which is quite simple to understand. It's basically the difference where we would like to get to the reference image. And the next step is then taking the derivative of the rendering equation from Kajiya. And thankfully, Mitsuba provides us the radiative backpropagation algorithm introduced in 2020 by Nimiya David and his colleagues, and the extended version of that by Vicini and his colleagues last year. So I will not really bother you with the whole details, especially of the derivative of the rendering equation. However, if you're really interested, I will definitely I would definitely recommend checking it out, either from our paper or basically typing in Google and writing differentiable rendering. With that, actually, let me continue with the problem and goals of our project. So the main idea, as you probably understand it right now, is getting the translucent material properties from a given set of reference images. But we also provide a tool for inverse rendering, basically for the data management process and etc. It's all that kind of stuff. But we also, in our paper, discuss a gradient-based optimization process, and also discuss work-forward data acquisition, so basically image acquisition and how to acquire initial scene as well. On the right, you can see our material reconstructions. On the left image, you can see the material reconstruction from synthetic data. And on the right, actually, material reconstruction from real-world data, alginate material from material research, which were provided to us from Technical University of Graz by Professor Starwich and his colleagues. With that, let me introduce the material parameters of interest. So I previously mentioned this X contains all type of information, scene description information. However, in our project, we have to further specify our parameters. Before actually I introduce them, but you can already see them, obviously. We proposed using two BSDF models. The first one is Disney's Principled BSDF, introduced by Burley and his colleagues, and the extended version of that actually in 2015, which includes integrated subsurface scattering. And the second proposed model is a rough dielectric BSDF by Walter and his colleagues, a fascinating paper. And we combine that with homogeneous part-speeding medium interior. So the material parameters of interest are then albedo, roughness, surface roughness, specular transmission, which originates from Disney's Principled BSDF, index of refraction, and extinction coefficient, which originates from homogeneous part-speeding medium. With that, let me switch to the problem statement. So here again, the material parameters of interest, we would like to optimize them. We define our task as an optimization problem. We introduce an objective function and try to get close to the provided reference images. What I never mentioned previously is the term H, which can be seen as box constraints, so trying to clamp the values in some between range for material parameters, for example. For RGB color, for example, we try to constrain the range into 0 and 1 per channel. With that, let me continue. So for our tool, we need two specific requirements. On the left, you can see the first requirement, which is a set of reference images. On the top, you can see the synthetic test cases. And on the bottom, actually, real-world alginate material, which were provided to us. And we photographed this real-world alginate materials in a texture box. And you can see the virtual version of that actually on the right-hand side, which brings me to the second requirement. This is really important. We need some scene descriptions for initial scene descriptions, so we can optimize the material parameters defined in the scene description. So on the top, again, you see the synthetic scene files, which can be done in Blender, and on the bottom, the real-world scene in virtual, such as in Blender. On the left, you see the virtual version of the texture box, and the right-hand side, the interior of that box. Okay. Let me now continue with our approach. So this is the user interface of our tool. We begin by loading a scene file and then continue by loading the set of reference images. Then we pick material parameters of interest, which can be done by double-clicking the leftmost column. And then we continue by optionally selecting hyperparameters. This can be like sample per pixel or iteration count. And in the end, eventually, if the tool doesn't crash, you can start the optimization. With that, let me continue with the optimization loop. So we initialize the selected material parameters with an atom optimizer. And for each camera pose, for each provided reference image, we take a differentiable rendering step, and we evaluate the objective function. Then we backpropagate the gradients using Mitsuba tree. Then we take another optimization step. Then we ensure legal values for the newly acquired material parameters. We, in the end, update the scene with these newly acquired material parameters. We repeat this process if the iteration count is reached or minimum error is reached. So basically, this is the computational part of our approach. And if you ever work with differentiable, any kind of differentiable rendering system, you would see a lot of similarities. Unfortunately, I don't really have too much time to talk about the experimental part of our approach, where how we acquired the images or scene description. However, if you're interested, you can check our paper. With that, let me switch to the results. So this is, in the slide, you can see a synthetic test case where we use Principled BSDF. The material parameters of interest are albedo, surface roughness, specular transmission, and index of refraction. And as you can see, in 100 iterations, we were able to get close to the provided reference images. On the next slide, I show another example. However, in this case, I'm using rough dielectric BSDF with homogeneous part-speeding medium. We are optimizing these parameters: albedo, roughness, extinction coefficient, and index of refraction. As you can see, we achieve quite acceptable results. So the idea with synthetic test cases is to test whether our approach would work, and we were quite happy with our results, which basically leads me to the real-world examples. So here you can see again the alginate materials on the right, the references. As previously, we use Principled BSDF, and the material parameters of interest are albedo, roughness, specular transmission, and index of refraction. However, compared to the previous example that I showed you, we are actually dividing the optimization process into two parts. In the first stage, which is until 49th iteration, we actually represent albedo as an RGB value. In the second part of the optimization, we change the representation of albedo into a bitmap texture and continue with the previously acquired material parameters and optimize to get close to the provided reference images. And as you can see, we are getting quite close to the provided reference images. Beware that this representation is actually a differentiable rendering step, so the samples per pixel value is quite low. That's why you see a lot of noise. So this is basically the result. There is a lot of things to improve. So for example, the bitmap texture contains a lot of information. So the shiny part that you can see on the top, on the blue one, actually doesn't originate from roughness or index of refraction parameters. That shiny part is actually contained in the bitmap texture, which is kind of troubling, but we would like to get better results in the future by better experiment with better image acquisition processes and better modeling, so that we can really bring the reality in the virtual scene so that we can really get good optimization results. With that, I think we are finished. Thank you very much for listening. You can find our paper in the CESCG website, and the GitHub repository is, you can see it over here, but you can also find the GitHub repository link in our paper. So thank you. If you have any questions, please let me know. I would really be happy to answer them.
So do we have questions from the audience? Please.
Thanks. So I have a question. I've seen in your slides that the initial kind of, or the initialization was quite simple in some terms. Have you had any problems with like finding a good initialization? Because we are using a first order method, so it might not converge in some instances, or was this not a problem for you?
I was kind of had luck with the parameters that I tried on, but in some cases it was difficult, and that's why I'm actually in my tool providing some interface so that the user, if the optimization process doesn't converge, the user then can say and restart the optimization with different parameter values, so the optimization can work better ways. I hope it kind of answers your question. So so this is a reusable tool, so you can test out different things. We solve this tool as more of for scientists who understand this process, and they can test out also different hyperparameters. So because in some of the examples that I had to choose different hyperparameters, such as samples per pixel, because the Monte Carlo integration process basically makes it difficult to converge in some cases.
Thank you.
So do we have more questions? Yes, please.
So right in this picture, you can see that for the loss function, you apparently had different options, but you only presented the L2 norm. So the first question would be, what other metrics did you test? And the second would be, how do they influence the convergence? Is it just a time thing, or does it really influence convergence?
That's a really good point. So there's actually what the main objective function we use is the dual buffer method introduced by Deng and his colleagues 2 years ago, I think, which basically takes two independent differentiable rendering steps in one iteration, which kind of helps with the convergence, especially if you use small samples per pixel rate. Otherwise, for other tasks, for example, for geometry reconstruction, I'm also trying to use regularization terms such as Laplacian loss, which might be in the future helpful to actually do this whole process, not really having an initial scene file, rather from basically using only reference images, such as a photogrammetry tool. And the second question was, sorry?
How it influences convergence?
The dual buffer method that we use, because it takes two differentiable steps, we were able to actually use lower samples per pixel rate, which helps us to get quicker results. So and interestingly, the dual buffer method kind of avoids the local minimas, and we kind of converge more quickly to the provided, we kind of get close to the provided reference images much quickly.
Okay, thank you.
Thank you.
So we have one more question over there.
Thank you. Thank you for the presentation. It was really interesting. When you showed that you went to a texture representation for the optimization for the real world scenario, so how, I was just thinking, like, what was the quality of that texture or the size? Because I see that you have like 6 scalar values for the optimization, and then you introduce, I don't know, like hundreds, thousands of more numbers in the texture to optimize for. So are those just like individual scalar values in a sense, and that introduce like hundreds more scalars to optimize for? Or did you have some, I don't know, more efficient texture representation, or was it like a function or something like that, or what was the resolution of the texture?
Mitsuba is such a good tool. It kind of allows us to make this whole process really generically. So we are basically, for bitmap, optimizing the bitmap texture, actually using some clamp values, so the color values don't go in some unfeasible range. So in this example, I'm actually using quite high resolution, 512 to 512, and from memory-wise, it was still acceptable, even though I had a bad GPU.
And even for the optimization, like that, introduced like thousands more parameters to take the gradient of. So
you can actually do that. It's a really challenging topic. So because the whole process also contains automatic differentiation, I wouldn't really recommend including all type of parameters. I would rather suggest using different stages to accomplish this different optimization for different parameters. So, for example, for index of refraction, introduces a lot of discontinuities into the process, and sometimes influences the convergence. So that's why in some cases we actually use two-stage optimization, where we actually optimize albedo, roughness, specular transmission, and in the second stage, we included index of refraction, and it was a more smooth process.
Thank you very much. It's really interesting.
Thank you.
I would have one more question. In the optimization process, you are trying to get as close as possible to the reference image. Some of the effects can be very much view dependent. It depends on the roughness, for example. So with the low roughness, you are getting more view dependence. So do you take into account like multiple reference images to solve for this?
Not for the real world test cases. Unfortunately, I didn't really have too much time didn't really have opportunity to take reference images. I'm complaining again, sorry. But for synthetic test cases, as you can see here, I have multiple reference images from 4 views. But you can actually go up until 12 images, 12 reference images. But one thing to note is obviously in the initial scene file, you need to be able to create sensors that matches roughly as in the reference images. But in our paper, we actually suggest this workflow where we use metashape to acquire camera positions so that so that if user wants to use multiple reference images, he would actually be able to get this initial state.
And if you use multiple reference images, you use some combined loss for these, or you process them independently? Or?
I process them independently. So it depends on the test, but in most cases I process them independently.
Okay. So maybe I have a last question. So can you elaborate a bit more on the rendering time? So we saw iteration counts. How long does one iteration take?
So I have a NVIDIA GPU 2080. It's an old one, and for this example, with 4 reference images, it took around 240 seconds. But please note that this is a physics-based rendering setting, so it's kind of actually normal, I would say.
Okay. So we have no more questions. So thank you again for a very nice talk.